All right, so let's continue our lecture on chapter 22 by looking at interaction between charges a little bit more carefully. And we're also going to look at the materials, how materials play a pretty big role as far as how these charges move within a material and how that gives us something called polarization and charging by induction. So we're going to look at what the material does with our charges. Okay, so let's start off with just by looking at separating two charges. So I'm going to have two plastic rods. One of these rods is going to become negatively charged. Actually, both of them are going to be negative charge. And I'm going to bring them together to see what happens. So this is essentially what happens. If you look back at the last video, that if you take a plastic rod and rub it with wool, you get a negative charge. And I briefly mentioned there that if you take a glass rod and rub it with silk, you get a positive charge. So both of these have charges, okay? And you can kind of see what, I think I actually have a next picture over there, but let me draw these in so we can see here. Okay, so this has a negative charge here. Negative, oh, sorry, these are positives. Positive, positive. And then this is the plastic rubbed with wool is going to give us a negative charge. Okay, so we have these two negatively charged objects in the case of the plastic and the plastic rods, or positively charged objects in the case of glass rods. So when you bring these two objects close together and they have the same charge, you have that repulsive force, right? So negative repulses negative, positive repulses positive. So I don't think that's a surprise to anyone. I think all of you understand that like charges are going to repel. But what we want to see there is that there is an electric force. So let's put it in terms of physics here, that if you see this interaction that we're talking about here, that these rods are this rod at least is being pushed away as you bring another rod of similar charge close to it, that there is a force acting on this rod. And because of Newton's third law, there's a force acting on this rod. So I could draw, I guess my forces in here. So there are these two forces. One force is going like this, and another force is acting like this. So equal and opposite, right? That's Newton's third law. There are these forces acting on these rods, and we call that force an electric force. Okay. Now, if I do opposite charges, how do those interact? So here's these. I just kind of switch the rods. So now I have a plastic rod and a glass rod after they've been charged up close together, and you see that because they have opposite charges, they're going to be attractive. Okay, so they have an attractive force between them. So kind of the same principle here, that there is an electric force that is determining how much, there's an electric force here pulling these two together if they have opposite charges, or pushing these two rods away if they have like charges. Okay, so electric force is attractive when charges are opposite, and electric force is repulsive when we're talking about like charges. Okay, so we know the sign of the charge matters, right? Whether it's positive or negative. But what about distance? What if we increase the distance between the rods? Well, that also plays a role. If I increase the distance between the rods, so here I have two negative rods, and so we would expect them to be repulsive. But if I increase the distance here, it's less attractive. And compare that picture to, let me go back a couple, to this picture. When that distance, let me call that distance, I don't know, R, I guess. Okay, that's my distance R. That distance is pretty small, and I get this repulsion. You can kind of see that angle that the hanging rod makes. So that at that distance, I get a certain force. Compare that to this distance now. That's definitely a larger distance here. The larger the distance, now the weaker the force. Okay, so there is a dependency on distance. The increased distance is going to weaken my force or decrease my repulsive force. And there is a dependency on distance. And what we're going to see is that that dependency, let me sneak it in here. Force is proportional. Let me make that a little neater here. Is proportional to 1 over r squared. Okay. So it's not okay, inversely proportional to distance, but inversely proportional to the distance squared. And this is summarized in something called Coulomb's law. Okay, so we're going to get to Coulomb's law in a bit, and we'll look at that extensively and calculate, plug in numbers and actually get an equation for force. But right now, I just want you to see the behavior. That if you have positive, if you have like charges, they're going to be repulsive. If they're opposite charges, they're going to be attractive. But not only that, we also need to consider how far apart these charges are. Okay, so I don't think a lot of this was new to you. Maybe the 1 over r squared was new, but in general, I think you all understand this behavior. All right, now let's look at materials. What does materials do? Well, materials really are going to make a huge impact on how these charges within a material move. So in general, we're going to have 2 materials. We have a conductor, which in a conductor, electrons, right, our negative charges, are able to move freely through the material. They're not bound to a particular atom. These electrons are free to move in the metal or in the conductor. And opposite of that is an insulator. So for an insulator, those electrons, and we talked about it in our last video, the valence electrons are going to stay close to their atom, close to their nucleus. Okay, so here's a good picture of it. So here is an insulator, and you can see that those atoms, you have the nucleus there, the core electrons in the I guess the darker green, and then the light green is the valence electrons. Okay, so remember that the light green is a valence. So those valence electrons are staying pretty close to their nucleus or nuclei. They're not moving around. Now look at the same picture, but for a conductor. Where's the valence electrons? Remember the valence electrons is that light green. The valence electrons are everywhere. It completely fills up that metal. So the electrons aren't bound to that to a particular nucleus. They're just free electrons. Another way you could think of it is that these electrons are almost like a sea of electrons or an ocean of electrons. They're just moving around in this metal, free to move however they wish. Okay, now there is also something called a semiconductor, and a semiconductor is there's a slight difference. It's kind of in between an insulator and a metal. A semiconductor could act like an insulator given certain circumstances, and then act like a metal or a conductor in certain circumstances. Pretty interesting stuff, though. I think our textbook talks about that if you want to look into it. But I'm just going to focus on these 2, an insulator and a conductor. Okay, so that's pretty much the general idea. So I have like this situation here where I have these 2 spheres, right? Sphere 1 is charged, sphere 2 is neutral. If I make a bridge by a metal, or in other words, use a conductor to make this bridge, if I do that, then the positive charges essentially now have a highway, right? They have a little path to get away from each other, right? These positive charges here are repulsed, and if there's a way for them to get away from each other and evenly distribute themselves away from each other, they're going to take it. And this is what happens when you do this, when you put a metal, or I guess a nail in this case, connecting these 2 spheres. The positive charges that were once here are going to be repulsed from the other positive charges, travel through the metal because they can, and go here. Compare that to the insulator. here's a piece of wood, which is an insulator. Those valence electrons will stay fixed on those atoms. And even though it's connecting these two spheres, the positive charges stay there. Right? The positive charges cannot use the wood to go to the other sphere. Okay. Okay, so let's look at a couple other scenarios here before I talk about induction. Let me do this. I want to look at something called polarization. So let me bring up my whiteboard here. Okay, so polarization uses this consequence of a conductor and an insulator. So let me start with two conductors. Or I guess just really one conductor. I'm going to start with this sheet of metal, which I'll put in blue. Oh, whoops. Okay, sheet of metal, and that we have let's start off with a neutral metal. So it's neutral. Oopsie. Okay, and what I'm going to do with this, I'm going to leave this neutral metal here. Now, of course, there's really positive and negative charges in there, right? Let me put positives in black and red. So I have a whole bunch of positives. Okay, and then the negatives. Now, realistically, you have those atoms and the electrons kind of moving around here. Okay, well, it's supposed to be neutral. I don't know, did I do it right? 1, 2, 3, 4. Okay. Way too many negatives. So I have 12 positives and I need one more. There. Yeah, neutral. Now, realistically, we have the atoms are going to be fixed, right, in their spaces, and the electrons are free to move. But I'm going to model these kind of like how I modeled the balloon in the last lecture, where we're just kind of looking at the net charge. Okay, so let's bring another rod. Let's make a positive rod. So I guess it could be a glass rod rubbed with silk. And I'm going to move it right here. Now, a glass rod rubbed with silk is going to have positive charges here. So what is that going to do to all these charges that are in this metal that's free to move? I should probably say this is a neutral conductor. I think I said that earlier, but let me write it. Okay. So what's going to happen to these charges? Well, these charges are going to rearrange themselves. So if I bring a positive charge close to this sheet of metal, this conductor, if I bring that positive charge there, what's going to happen? Let me erase all this stuff. All the negatives are going to be attracted to it. Okay, so you're going to have a lot of negatives here. I think I did my negatives in black. Okay, and then on the other side, so all the electrons went to the left. That means on the right side is you have essentially no valence electrons covering those atoms. So on the right side, it's all positives. Okay, there's no valence electrons for these atoms here. All the valence electrons that would have canceled these out have moved this way. Now overall, I still have a neutral sheet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oops. Let me put a couple more positives just to make it 1, 2, 3, 4, 5. Oops. 6. Okay, so overall, it is still neutral. I haven't gained charge on the conductor. I haven't lost charge on the conductor, but I do have a separation of charge. And so what this does is gives us that separation of charge is what polarization does. Polarization separates the charges, and now you have a polarized object. Okay, so now we have, if we think about it a little bit more here, not just a separation of charge, but now what's going on here? You have all these negative charges, all these positive charges, Well, now we have a force between them, right? And this is called a polarization force. So we have a force, an attractive force between these two objects. Force going that way, and a force going this way, right? So let me, it's supposed to be equal and opposite. Okay, so this is called a polarization force. Okay, because now you have those two opposite charges, right? The positive and the negative, and they're so close to, they're pretty close together, right? Whatever this distance is, but they're pretty close together, and so they're going to be attracted to each other. Now you could argue, well, what about these positives here and these positives over here? Well, those are repulsive, right? They are repulsive to each other, but they have such a larger distance between them that repulsive force that these two are going to exert on each other is going to be way smaller than the attractive force that these two have on each other, these positives and these negatives have on each other. Okay. All right, now what about, let's look at a different scenario. I'm gonna look at something pretty similar. I'm gonna draw another rod. And I'm gonna draw another sheet here. I'm gonna do this sheet in, let me just do it in black, I guess. Okay, now this time, I'm gonna have not a neutral conductor, but a neutral insulator. And kind of the same idea. I'm going to bring that rod on the left is going to have an overall positive charge. Okay. What's going to happen to the insulator? Am I going to have a polarization force? So remember what an insulator does. An insulator, let's go back to that the picture I had here. Here's the insulator. Insulator does not allow its electrons to move, right? Or at least does not allow the valence electrons to move away from the parent nucleus. Okay, so given that, will I have a polarization force in my picture here? Well, you actually do. You actually do have a polarization force. And it's like, well, how can that be if the electrons can't move around? Let me draw it this way. Let's look at each atom here. If I look at, let me pick a different color. I'm going to pick, do this in blue. So if I look at an atom over here, far away from it, the atom far away is going to have its nucleus in the middle and the valence electrons are around it, right? So it's not really going to change here. If I compare that to a atom closer to the rod, it's not going to look the same. It's going to have a different shape. So the shape's going to look something like this, a little bit more elongated. And the reason why it's going to be elongated is because the valence electrons, though it is still bound to the parent nucleus, the valence electrons are going to go away from the nucleus because they're attracted to that positive rod. So these valence electrons are going to be moving a bit this. And you get what's called a dipole. A dipole is when you have two opposite charges separated by small distance, and that's what we see here. Okay, and we're going to see a whole bunch of these dipoles. So let me draw a couple more. Maybe one like this, one like this, and you have your negative charges and your positive charges. So if you look at this, the negative charges are closer to the positive charges. Let me say it this way. The negative charges are closer to the rod, right? So these negative charges closer to the rod than the positive charges, right? So because these are closer to the rod, they're going to give you a greater force, a greater attractive force than the repulsive force between this positive and this positive, for example. Now, what happens to this dipole as you start to go further away from it? Well, as you start to go further away from it, that dipole is going to start to get a little weaker. So maybe not as elongated as, I'll try my best to draw it. And it starts to get more like a circle. Okay, so you start, that dipole starts to kind of, I guess, weaken. The negative charges start to get a little bit closer to the positive charges. And then even over here, you have a slight separation, but not as obvious. Oops. Okay, until you're on the far right of the sheet, and then you don't have really any separation at all. It just looks like a regular. I mean, you might have some subtle polarization going on. But the valence electrons are essentially around the nucleus, so you don't really have that much polarization there. But as you get closer to the atom, closer to the rod, I should say, as you get closer to the rod here, you definitely start to see that greater polarization, and that gives you a net force going this way. So you get a net force. Okay, so just because we're looking at an insulator, it doesn't mean you have no polarization force. You still do. I mean, it's going to be smaller than the polarization force between a conductor and a rod. So this force here is greater, despite, ignore the length of my arrows, but this force here is greater than the force down here. Okay, because this polarization is more extreme, right? The polarization is overall through the conductor, whereas this polarization is only, on the atoms closest to the rod. Okay, so that's polarization. Now there is one other way of charging an object. Now, okay, I should say one more thing though before I leave polarization. After even all this, I still have an overall neutral insulator. And same thing with here. With my conductor, it is still overall neutral. I didn't gain or lose electrons. I just simply moved them around. Okay, so it's still an overall neutral object. Okay, now I could make this positive or negative depending on what I do with it, and this is what's called my induction of charge, or charging by induction. Okay, so it's a process to do. So in order to do this, well, I already talked about this, that you have. Oh no, I didn't have that. So if you bring charge, here's another difference between an insulator and a conductor. If you bring charge to a conductor, because charge is free to move in a conductor, that charge is going to distribute themselves on the surface, so that all the charges there are at equilibrium. So let me show you what I mean by that. So you can see like a picture here. So let's say I have a rod or a sphere. Let's say it was a sphere. Okay, here's a sphere, and I'm going to put a whole bunch of positive charges. Okay, so I have a whole bunch of positive charges in a rod, let's say, and I'm going to put it here. Okay, when I do that, the positive charges are going to start to disperse themselves around here in such a way so that, in a pretty quick amount of time, you're going to have a sphere with the charges evenly spaced around it. Okay, and the reason why they want to evenly space is because each charge is going to feel a zero net force. Each charge is going to be in equilibrium. So this charge, let's just pick one charge. Let's look at this charge really quick. This charge has a repulsive force from this guy, repulsive force from this guy, or repulsive force from that guy. And then, we're talking about a sphere, so it's three-dimensional. Behind the sphere, since we're only looking at one face of it, on the other side of the sphere is another positive charge that's pushing away from it. So you have all these forces pushing in all directions here. And when you have all these forces pushing in all directions, your net force is going to be 0. So this is called electrostatic equilibrium. And it's essentially saying that all these charges here, every single charge is going to have a net force of 0. Okay, so when that happens in a conductor, the charges are spacing themselves evenly around this conductor, especially if you're talking about a sphere, around the sphere in order to maintain this electrostatic equilibrium. Okay, so that's what's going on here. As I bring this charged plastic rod, which I guess a plastic rod would have negative charges, the negative charges will disperse themselves evenly around this metal sphere. If I connect these two metal spheres together by a plastic rod, nothing's going to happen, right? We talked about this earlier in an earlier slide. Okay, so this metal one, the one that got the charge in the first place, is just going to keep that charge, and this one's going to stay neutral. If I connect it with a metal rod, because it's metal, the charges are going to disperse themselves evenly around this whole thing, around this metal sphere, and even along the metal rod. Okay, so the charges are going to disperse themselves evenly so that electrostatic equilibrium can be maintained or can be reached. Okay, so that's another key difference between conductors and insulators, that you don't see this rearranging of charges with an insulator, because remember, in an insulator, charges can't move freely. But in a conductor, they can move freely, and so they will rearrange, and you get that electrostatic equilibrium. Okay. So keeping that in mind, that we have charges moving around in conductors, there is a way we could charge these conductors. So let me show you this way. So this is what charging by induction is. Let me show you. Okay, so let's say I have a neutral sphere, and I bring a positive charge or a positive charge rod to it. And we talked about this already, that what we're going to see is polarization, right? So if you have a positive rod here, all the negative charges are going to be attracted to it and leaving behind positive charges on the other side of the sphere, right? And again, this has to be a conductor. This wouldn't work if this wasn't a conductor. Okay. Okay, so we have this conducting sphere. It starts off neutral, right? Neutral. And then we have the separation of charge when we bring a positive rod here. Okay. Now, if I connect this to something called a ground wire, what does a ground wire do? A ground wire is going to essentially connect it to the earth, where it will allow any excess electrons to go to the earth, or it could get electrons from the earth. So, for example, here, if I have, here's this neutral rod, here's the ground, and here's like the symbol for ground wire. If I bring a negatively charged rod to here, those electrons that were once sitting in here in this conducting rod are going to be repulsed from this negative rod, and the electrons are going to run away from it and go to the ground. And you take away this rod, and what's left? What do we have left over? It's just a positive charged rod. So I started with a neutral rod, got rid of the electrons because the electrons had somewhere to go, and now I'm left with a positive rod. And notice that this is not connected to the ground anymore. Okay, so that is a way to charge up these rods. I didn't rub anything together like I did before. This is charging by induction. Okay, there's another way of doing this, and that is by this thing called an electroscope. So electroscope is pretty handy because these two leaves here, they're very, very light, don't weigh very much. So if these two leaves have the same charge, you're going to see them push away from each other. They are going to be repulsive, and so you'll see the leaves kind of spread out from each other. You'll see the angle between them increase, in other words. Okay, so let's say I start with a neutral electroscope. So here's my electroscope. All right, it's the same picture here. You have the metal ball here and the leaves. So here's a metal ball and the leaves. And if I bring this positive charge here close to the electroscope, well, the positive rod is going to attract negatives to the ball, to the top of my electroscope. And what if the negative charges go up, that means I have positive charges below. So where you're going to see these leaves spread out. Now, in this picture here, I actually make contact here, and that those negative charges jump on the rod, and now I have an overall positive charge from my electroscope. Okay, so this isn't charging by induction. This is just conduction. You're physically touching this rod to the electroscope, and then now you're left with a positive electroscope. Okay, now induction is a little different. Induction is a process. So let me actually draw it out, because I think the process is better if I draw it. All right, so I'm going to do it a little differently than what I have on the notes there. Here's my electroscope, and here are the leaves. Draw the leaves and that. Okay, so if I bring, I'm going to do one more thing here. I'm going to connect this rod to another rod, or to another sphere. Okay, so I have all these spheres here, the electroscope here, the sphere here, and I'm going to bring a rod, another rod. Where is, I guess I'll just draw it. Close to it, not touching it, but I'm going to bring a rod close to it, and that rod is going to have positive charges. So positive charges. Now, if I bring a positive charge close to this contraption here that I have, what's going to happen to the charges here? Well, if I bring a positive rod here, all the negatives from here and from here are going to be attracted to this rod. So I'm going to have a gathering of negative charges here. Okay, so I have all these negatives there, and if I have all the negatives being attracted to the rod, well, where did those negatives come from? Those negatives came from the other parts of the this contraption here. So it came from the leaves. So that means I have a positive charge on the leaves now, because those leaves just lost electrons. Right, those electrons moved upwards, and I also have positive charges here. Okay. Okay, so this is just polarization. Okay, we talked about this already. Now, the next part is where the induction comes. So I guess I have to draw it again. So I'm going to redraw my little picture here. Okay. And my leaves. And then another rod here. Oh, wrong color. Okay, so what am I actually going to do here? So I still have my charges. I have my charges here. I still have my rod as before. Again, not touching. And I have all these positive charges here, all these positive charges here, all these positive charges here. Now, what has happened here when I did this polarization? This thing has way more negative charges than these positive charges. These negative charges came from the bottom, but also came from the sphere, right? So now I have all these negative charges on on my electroscope. So I'm going to take away this thing here. If I break this off, now my electroscope has an excess of negative charges compared to these positive charges down here. And I don't count them. I guess I could do more. You know, if you're going to start counting them, you would have more new. Oops. Okay, so if I break this off now that thing's gone. This little thing that I added to my electroscope, that's gone, and I still have this here. I'm going to take away these two. So first I broke off the extra sphere. Okay, and that's what we didn't really do anything to the charges. We just took it away and took this away. And then now I'm going to remove the extra sphere and rod and the charge rod. What happens then? Well, if I take those things away, okay, so I'm going to have my rod or my electroscope here and my leaves. Gold leaves. What happens to those electrons? Well, those negative charges here that I start out, if I take these away, these negative charges are going to disperse evenly through themselves. Now, I am going to lose some. So some of these negative charges are going to neutralize these positive charges, but I still have an overall negative charge here. Right? I have more negatives than I have positives down here. So that negative charge is going to distribute themselves because of electrostatic equilibrium, because these are conductors, and you have negative charges kind of throughout here. All right, spaced evenly throughout the whole electroscope. Okay, so this is called charging by induction, that we induced a charge, a net charge by this process. All right, so that's what I explained here. It's kind of the same explanation. I actually like my picture better, but very, very similar. Actually, no, this is just what's called polarization here. All right, so let's try this, a couple examples, and then we'll wrap up this introduction to charges. So metal sphere 1 and 2 are touching. Both are initially neutral. All right. The charge rod is brought near. Okay, so that's the charge rod. First gets brought near. Then the spheres are separated. The spheres are separated, and then the charge rod is then removed. So let me do this. Let me draw each step. So this is step A, right? Get my pen out. And in step A, we just have really polarization. Negative charges are attracted to the positive, and positive charges are repelled. 1, 2, 3, 4, 5. Okay. Now, overall, these two spheres total, these two spheres here are still neutral, right? Having all these negative charges equal to the amount of positive charges overall. So it is still neutral when they're in contact. Now, part B, it says the spheres are then separated. So the rod is still there, I believe. It didn't say anything about the rod. So I still have the rod here. Positive charges. And then I have these spheres, but they're separated now. Just slightly separated so that they're not in contact. So now I still have negative charges here. And I also have positive charges here. And then part C, I remove the rod. So now it just has the spheres. Now, if I remove the rod, this negative charge is not attracted to anything. Okay, so this negative charge right here, there's nothing attracted to it, right? If I take out this rod, these negatives are still negative, but now they're going to disperse themselves evenly around the sphere here. And same thing with this positive charge. That this positive charge here, you take out the rod, there's nothing repulsing it anymore. And so now these positive charges will distribute themselves evenly inside that sphere. So sphere 1 became negative, sphere 2 became positive. Okay, so that's the answer here. I've asked what happened to this. Sphere 1 is negative, sphere 2 is positive. Okay, so this is another example of charging by induction. We use polarization to separate the charges, and then we did something physical. We physically separated the two spheres, right? Sphere 1 and sphere 2. Okay. Let's do this one. This one's get some numbers in here. So maybe let's see what's in it. Yeah, and we'll stop there. So identical spheres are initially charged as shown. Spheres P and Q are touched together and separated. Then spheres Q and R are touched together and separated. Afterwards, the charge in sphere 1 R is what? Okay, so a couple of process here. For each process, I want to draw out the process, and then and we'll see what's left over. So let's do the first step here. So the first step, spheres P and Q. So we know they're conductors, right? They're metal spheres. So they are going to be able to exchange charge, or the charge will distribute themselves evenly among the two spheres. So P and Q touch together. Let's see what happens when they're touched together. I'm going to actually draw this out on the whiteboard here. So got P, Q, and they're identical, so they're all the same size. So P starts out, this is P, Q. Let's see, P starts off with what? Starts off with a positive 4 nanocoulombs, which I'll talk about with positive 4. And charge is negative 2. Now it does say, I haven't introduced it because we haven't talked about Coulomb's law yet, but the unit for charge, good place to introduce it. Unit of charge called a coulomb. Okay, and we're typically 1 coulomb is a lot of charge. Usually we use nanocoulombs. So if you see nanocoulombs, NC, and we're talking about 10 to the negative 9 coulombs, or sometimes we see microcoulombs, which would be 10 to the negative 6 coulombs. Okay, so those prefixes come up a lot, nanocoulombs and microcoulombs. So that's just a unit of charge. So on P, we have positive 4 nanocoulombs. On Q, we have negative 2, and we're going to bring these two together. So if I bring these two charges together, okay, so now they're in contact. If this one had positive 4 here, oops. So I'm just going to do 2 positives. And the Q had 2 negatives. We combine them together, and what's going to be left? Well, the 2 of these positives here, 2 of these positives are going to neutralize these 2 negatives. Okay, so what's left, if you add these together, total, you're going to have 2 nanocoulombs. So add these together, gives you a positive 2 nanocoulombs, but that positive 2 is shared between these 2 spheres. So you're going to have 1 here and 1 here. Well, I guess I'll do it in red. Okay, so look at what happened. Positive neutralize these 2 negatives. So that gets rid of this and this. Okay, so I guess I could erase that if you want. And then now, these 2 positives that are left over are going to distribute themselves between these two spheres. So this is still sphere P and Q, right? Sphere P and Q. Okay, that's what happens when you put P and Q together. Now, what does it say next? Now it says Q and R are touched together and separated. So look at R. R is a -1 nanocoulomb. Okay, so let's go back here. If I separate Q now, so Q has a, I guess a positive. Yeah, positive. Yeah. Almost lost track of that. So positive, and R has a negative, right? Is it -1? Just double check there. Yeah, R is -1. So here's a +1 nanocoulomb. After we combine it and separate them, we're left with a +1, and R we're told is -1. So you combine these together, and we get 0. So when you combine these two spheres together, if you want to see it in a picture here, well, these two charges are going to combine. In this case, this charge will neutralize this charge, and now P and Q have no charge on them. So no, sorry, Q and R. This is Q and R. They're completely neutral. The charge is neutralized. So at the end of the day, I have P was left with a charge of +1. Q has no charge, and R has no charge. After I do all these combinations. Okay. So the question is, afterward, what is the charge on sphere R? Well, saw that it was going to be 0 nanocoulombs. All right, so that is charge. You can see materials do play a big role, whether we're talking about conductors or insulators. And what we're going to talk about next time is the attractive force. What is the force between these two charges? And this is where Coulomb's law comes in. So we're going to dive into this equation, and we're going to start doing some numerical calculations. Just to give you a heads up, guys, vectors, very, very important. We're going to be using vectors a lot. So if you need to review, look over adding vectors by components, splitting vectors into components and adding them together, because we do that quite a bit in this course. All right, so we'll talk about that next time.